In this lesson, we're going to learn about roots and rational exponents. Let's start out with the terminology, the principal nth root of a number. We would call this the principal nth root of a. And if the principal nth root of a is equal to b, this means that if you take b and raise it to the nth power, you get a. And I think this will be easier to understand when we look at examples involving actual numbers. And we'll do that shortly. We call n the index. So this n is called the index. For this example here, our index is this little number here, 3. And a, which is the quantity underneath the radical symbol, is called the radicand. So in this case, a is the radicand. In this example here, 27 is the radicand. We call this symbol here a radical symbol, as it says here, and we call the whole thing a radical. Now let's look at some examples of principal roots involving numbers rather than symbols like we see here. Now, formally, we should call this the principal cubed root of 8, but mathematicians often shorten it and just say the cubed root of 8. So from now on, you'll often hear me drop the word principal and just refer to something like this as the cubed root of 8. If the cubed root of 8 is equal to 2, this means that if you take this 2 and raise it to the index, the 3, we get the radicand, which is 8. So if somebody tells you that the cubed root of 8 equals 2, that means that 2 cubed equals 8. Let's look at another example. Now this little green number here we call the index. If there is no index written, you always assume it's a 2. So if you do not see an index, that means that the implied index is a 2. So I'm going to rewrite this with the implied index, which is 2. Both of these are equivalent. Since the square root is so commonly used in mathematics, mathematicians have agreed that we can drop this little index when it's a 2 and just write it like this, and we'll all know that the implied index here is a 2. So if we say that the square root of 100 is equal to 10, this means that if we take this number, 10, and raise it to the index, 2, we get the radicand 100. So again, the square root of 100 equals 10 means that 10 squared equals 100. Next, we're going to look at two important rules. To start, if the index is even, the radicand cannot be negative. So let's look at some examples. Let's say you have this expression here. What is the implied index here? Well, remember, if there's no index written, you can always assume it's a 2. We can even write the 2 here just to make that extra clear. Now notice, the index is even and the radicand is negative. When that's the case, there is no solution in the real number system. Let's look at another example. Here, the index is even and we have a negative radicand. When that's the case, there is no solution in the real number system. Here's one last example. Again, here the index is even and the radicand is negative. When that's the case, there is no solution in the real number system. Why is that the case? Well, let's try to find a solution for this example here. What is the square root of negative 25? Again, normally when the index is a 2, we don't write it. So for your final answer, if you have a radical with 2 as the index, we can drop the index, but I'm just writing it for this example just to be extra clear. So we're trying to find out, what is this equal to? Well, if the square root of negative 25 is equal to some quantity, that means that we should be able to take that quantity and square it to get the radicand, negative 25. Now, can you think of a number that when you square it, you get negative 25? No, that's impossible, because anytime you square a number, you get a positive result. So it's impossible to square any number and get a negative 25. So that means that there's no solution here. What if we tried to find the solution for this example? So we want to know, what is the fourth root of negative 16? Well, let's say it's equal to some unknown quantity, and that means that whatever the answer is, we should be able to take that answer and raise it to the fourth power to get the radicand, negative 16. What number raised to the fourth is equal to negative 16? Well, if you raise any number, positive or negative, to the fourth power, you will always get a positive result. It's impossible to raise a number to the fourth power and get negative 16. So both of these examples have no solution. That's because it's impossible to raise a number to an even power and get a negative answer. And remember, this expression can always be written in this form. So anytime you have an even index, if you have a negative radicand, there will be no solution in the real number system. Now, we just explored examples where the index was even. What about if the index is odd? If the index is odd, the radicand can be positive or negative. Let's look at some examples. This expression will have a solution. Here's another example where the index is odd and the radicand is negative. This will also have a solution. You could also have an odd index and a positive radicand, and that expression would have a solution. Because when your index is odd, you're allowed to have positive or negative radicands. Let's look a little bit closer at why we have a solution if the index is odd and the radicand is negative. So I've just copied down this example right here. Now we're trying to figure out what this is equal to. Well, if the cubed root of -8 is equal to some quantity, that means that we should be able to take that quantity and raise it to the cubed power to get the radicand, which is -8. Is there any number that when we cube it, we get -8? Yes, in fact, if we take -2 and cube it, we get -8. So there is a solution here. The solution is that the cubed root of -8 is -2 because -2 cubed equals -8. So when your index is an odd number, like 3, 5, or 7, your radicand can be negative or positive. Because we see here our radicand is negative, and when we rewrite it in this form, it's possible to raise a number to an odd exponent and to get a negative result. So we do have a solution here. Now before we move on, let's quickly talk a little bit more about the term the principal nth root. You might be able to just solve this problem very quickly in your head, but I want to look a little bit closer at the answer here. So this is the square root of 36. So just for clarity, I've rewritten this problem and I've included the implied index 2. Now the square root of 36 is equal to 6. We know that this is true because this means that if we take 6 and raise it to the index, a 2, we get the radicand 36. And since 6 squared does in fact equal 36, it must be true that the square root of 36 is equal to 6. But you might be asking yourselves, is there another solution to this problem? Could the square root of 36 also equal -6? Well, let's see. If this is true, this means that when we take -6 and raise it to the index, which is a 2, we get 36. And this is true. -6 squared does equal 36. So is the square root of 36 equal to 6, or is it equal to -6, or is it equal to both? Well, an expression written in this form is called the principal nth root. So we call this the principal square root of 36. When you're calculating the principal root of a positive radicand, we always assume that we're looking for the positive answer. So if your radicand is positive, you're going to only give the positive answer. So I'm going to cross this out because mathematicians have defined the principal root of a number to always be positive when your radicand is positive. If a mathematician wanted both the positive and negative solution, we would write plus or minus the square root of 36. If you see a plus or minus in front of your radical, then you can assume that we want both the positive and negative solution. But if you don't see a plus or minus out front, you can assume that when your radicand is positive, we only want the positive answer. So now we're going to practice solving problems involving radicals by hand. While you may be able to just type these problems into your calculator and get an answer right away, we're going to soon look at radicals that involve variables. And your calculator won't give you an answer to a problem involving a variable. So in order to prepare for those types of problems, it's very important that we practice solving these problems by hand. Let's start with the fourth root of 81. We can say that if the fourth root of 81 is equal to some answer, that means that when we take the answer and raise it to the fourth power, we get the radicand, which is 81. So now we have to ask ourselves, what number raised to the fourth power is equal to 81? And we can use our calculator to support us in finding this. You might have to try out a few numbers. If you take 2 to the 4th, either mentally or on your calculator, you'll get 16. So 2 doesn't work, but if you take 3 to the 4th, you get 81. So since 3 to the 4th is equal to 81, that means that the 4th root of 81 is equal to 3. Let's take a look at another example. Now, if you notice that your radicand is negative, you want to pause for a minute to ask yourself, is there a solution? Let's look back at the previous page. We said if the index is even, the radicand cannot be negative. If the index is odd, the radicand can be positive or negative. You'll have a solution either way. The index in this particular problem is odd. If the index is odd, then the radicand can be negative. So it looks like we'll have a solution here. To find the solution, we can say that the cubed root of negative 125 is equal to some answer. That means that we should be able to take this answer and raise it to the 3rd power to get the radicand negative 125. So now we need to ask ourselves, what number cubed equals negative 125? And you might have to try a few numbers in your calculator. Try negative 3 cubed, try negative 4 cubed. Once you try negative 5 cubed, you'll see that negative 5 cubed is equal to negative 125. So since negative 5 cubed is equal to negative 125, that means that the cubed root of negative 125 is equal to negative 5. Now, remember, whenever you see a negative radicand, you want to pause for a second to ask yourself, is there a solution? Since there's no index written here, the implied index is a 2. And if the index is even, the radicand cannot be negative. You could try to use this process to find a solution, and you'll get stuck. You won't be able to find the solution. So when the index is even, if you notice that your radicand is negative, that means that there's no solution. And notice for our solution, I've written no real solution. Later on in chapter 6, we'll learn about the imaginary number system. And this problem actually does have a solution in the imaginary number system, but for now, we're only working with real numbers. And this problem has no solution in the real number system. Another way you could state your answer is that this is not a real number. Next problem, we notice that the radicand is negative, so we should pause for a minute to determine if there's going to be a solution here or not. Since the index is an even number, 6, the radicand cannot be negative. That means that there's no solution. Let's take a look at problem number 6 here. We're trying to determine what is the 5th root of 1 over 32. Well, we can say that if the 5th root of 1 over 32 is equal to some answer, this means that we should be able to take that answer and raise it to the 5th power to get the radicand 1 over 32. So now we have to figure out what number raised to the 5th is equal to 1 over 32. Well, if we're getting a fraction, that means the number that we raise to the 5th power must be a fraction. And remember, when you raise a fraction to an exponent, we apply that exponent to the numerator and to the denominator. So let's ask ourselves, what number raised to the 5th gives us 1? That would be 1. Then we can ask ourselves, what number raised to the 5th gives us 32? And you might have to try a few numbers on your calculator. When you take 2 and raise it to the 5th power, you'll see that you get 32. So since 1/2 raised to the 5th equals 1 over 32, that means that the 5th root of 1 over 32 is equal to 1/2. Now, for this example here, I noticed that we have a negative radicand, so we need to pause for a second to ask ourselves if we'll have a solution here. Notice the index here is an odd number. If the index is odd, the radicand can be negative, so we will have a solution here. And we can say that if the cubed root of negative 27/64 is equal to some answer, that means that when we take this answer and cube it, we get the radicand negative 27 over 64. Notice I moved this negative up to the numerator. Often when you're doing calculations in math, if you have a fraction with a negative out front, it makes the calculations easier if you move the negative to the numerator. So we have to figure out what number cubed gives us negative 27 over 64. Since we have a fraction here, that means that we're going to be cubing a fraction as well. So let's look at the numerator first. What number cubed gives us negative 27? If you take negative 3 and cube it, you get negative 27. Next, let's look at the denominator. What number cubed gives us 64? if you take 4 and cube it, you get 64. So, since negative 3/4 cubed is equal to negative 27 over 64, that means that the cubed root of negative 27 over 64 is equal to negative 3/4. And for your final answer, you can put the negative in the numerator or out front. Let's take a look at one last example. Now notice we have a negative out front here. Just temporarily, I'm going to ignore the negative and focus on the 6th root of 4096. So let's first compute the 6th root of 4096, and we'll add this negative back in just a minute. So we can say that the 6th root of 4096 is equal to some quantity. That means that we should be able to take this answer and raise it to the 6th to get 4096. So now we have to figure out what number raised to the 6th gives us 4096. You'll probably have to try several numbers in your calculator. Try 2 to the 6th, 3 to the 6th. Once you try 4 to the 6th, you'll see that that equals 4096. So, since 4 to the 6th equals 4096, that means that the 6th root of 4096 equals 4. So, we're ignoring this negative for the time being, and we said that the 6th root of 4096 is equal to 4. Now, since our original problem has a negative out front, we need to add that negative to our answer as well. And you could think of this negative as a negative 1 times the 6th root of 4096. We found that the 6th root of 4096 is equal to 4. So this quantity is equal to 4. So we want to take negative 1 times 4, which equals negative 4. Now, drawing these pink boxes is an effective way to solve problems involving radicals. But we're going to soon get into much more complicated problems. And drawing these pink boxes for those more complicated problems can get a bit clunky. So on the next page, we're going to learn a shortcut that we can use for solving problems like these. And for the shortcut, we're not going to have to draw these pink boxes like we drew here. On this page, we're going to learn a rule. And then on the next several pages, we'll learn how to use this rule as a shortcut for solving problems involving radicals. Remember that we've used n to represent our index. If the index n is even, and if you have a special situation where the index matches the exponent underneath the radical, then this is equal to the absolute value of a. If, on the other hand, the index n is odd, when you have the special situation where the index matches the exponent underneath the radical, this is equal to a. Now that we've written down the rule, let's look at some examples. First, we're going to look at an example when the index is even. And first, we're going to compute this problem using what I call the long way. This is the method involving the pink boxes that we learned on the previous page. If we're trying to compute the 4th root of negative 3 to the 4th, let's first simplify this radicand. Negative 3 to the 4th is equal to 81. So we could rewrite this as the 4th root of 81. Now I'm going to pause for just a minute here because on the first page we learned that if the index is even, the radicand cannot be negative. So some people look at this problem and they say, uh-oh, the index is even and the radicand is negative, so that means that there's no solution. But the radicand here is actually not negative. The radicand is this whole expression underneath the radical, negative 3 to the 4th. And if you actually compute negative 3 to the 4th, you get positive 81. So when we actually compute the radicand, it's a positive number here. So we are going to have a solution here. Now to compute this the long way using those pink boxes, you'll find that 3 to the 4th equals 81. So that means that the 4th root of 81 is equal to 3. Now let's solve this problem in a quicker way using this rule. I've just copied down this original problem here. Now, when you have the special situation where this index matches this exponent, then you can use this rule here. And this rule says if your index is even, which is the case here, then your answer is equal to the absolute value of a. So here, our index is even, so the answer will just be the absolute value of a, which is negative 3. And if we take the absolute value of negative 3, that gives us 3. You can really think about it as the 4th root and the 4th exponent cancel each other out. So the 4th root and the 4th exponent are inverse operations. They cancel each other out, just leaving us with negative 3. But when this is an even number, we just have to make sure to put absolute value bars around our answer. Now, when this number here is even, why do we need these absolute value bars? Well, when this number here is even, this quantity underneath the radical will always be positive because any number raised to an even number gives you a positive result. And when you take the root of a positive number, you always get a positive answer. So our answer needs to be positive, and we ensure our answer is positive by using these absolute value bars. Next, let's take a look at an example when the index is odd. And let's first solve this the long way using these pink boxes. Let's start by computing or simplifying this radicand. -2 cubed gives us -8. Now, remember when our index is odd, we're allowed to have a negative radicand. So we will have a solution here, and you'll find that -2 cubed equals -8, so that means that the cubed root of -8 is equal to -2. Now let's solve this using the shortcut, which involves this rule here. So I've started by copying this original problem over here. Now the shortcut says that when the index matches this exponent, if the index is odd, the answer is just a. So here the index is odd, so our answer is just a, which is -2. And when the index is odd, we do not put absolute value bars around our final answer. So our final answer here is -2, which is the exact same answer we got using the longer approach. So again, the cubed root and the cubed power are inverse operations. They cancel each other out. So you can think of the cubed root canceling the cubed power and just leaving us with -2. When this index is odd, we don't use absolute value bars around our answer. On the next page, we're going to see how this rule allows us to solve problems very quickly. So, if you have this special situation where your index matches your exponent, we can use the rule from the previous page. And the rule says that the fifth root and the fifth power are inverse operations. They cancel each other out. And so if the fifth root cancels the fifth power, that leaves us with z, but we have to decide if we use absolute value bars in our answer. Remember, when the index is even, you need to put absolute value bars around your answer. When the index is odd, you don't put absolute value bars around your answer. Since the index here is odd, we do not put absolute value bars around our answer. So our final answer here would just be z. Here, there's no index written, so we can always assume that the implied index is a 2, and I'm going to write it just for clarity. Since the index matches this exponent, we can use that special rule, and that special rule tells us that when these numbers match, they're inverse operations and they cancel each other out. So the square root and the square cancel each other out, leaving us with this quantity here, -9, but we have to decide if we need absolute value bars or not. When this number is even, we need absolute value bars. So I'm going to add absolute value bars around our answer, and then we need to simplify this. The absolute value of -9 is equal to +9. And if you think about it, it makes sense, because when you take -9 squared, that gives you a +81. And the square root of +81 gives us +9. We can use the rule here. Since these two numbers match, they're inverse operations and they cancel each other out. And if we cancel the fourth root and the fourth power, we're just left with n-3. But we have to decide if we need absolute value bars. Since this is an even number here, we need to put absolute value bars around our final answer. Here we have a negative out front again. I'm going to kind of just leave this negative off to the side and focus my attention on this problem here. So, since these two numbers match, they're inverse operations and they cancel each other out. And the sixth root will cancel the sixth exponent, leaving us with -2. Now, do we need absolute value bars here? Yes, because this is an even number, so we'll add our absolute value bars. And now I've been ignoring this negative out front, but let's just keep bringing this negative out front. Now, let's see, we can continue bringing this negative down, and then the absolute value of -2 leaves us with +2. But this negative out front makes our final answer -2. Now, in these next two problems, we're going to see how we're going to use this rule that we've been practicing throughout the rest of the chapter to solve problems involving radicals instead of drawing those pink boxes that we were drawing before. So to solve this problem here, notice we can't yet apply the rule that we've been practicing because there's no exponent underneath here to match this index. Now, we learned before to solve these types of problems by drawing those pink boxes, and you could use that pink box approach to solve both of these. But a quicker and more condensed way to solve these types of problems is to use this rule. I've started by just drawing the fourth root. Now, in order to use this rule that we just learned, we need this index to match the exponent underneath the radical. We need to figure out how to rewrite 625 as some quantity to the fourth. So try it on your calculator. Try 3 to the fourth, 4 to the fourth. Once you try 5 to the fourth, you'll see that 5 to the fourth is equal to 625. So we've written an equivalent expression here. 5 to the fourth is the same as 625. But by rewriting it this way, we can now use the shortcut that we just learned. Since this index matches this exponent, they're inverse operations and they cancel each other out. So the fourth root cancels the fourth power, leaving us with 5. Technically, since this is an even number, we put absolute value bars around our answer, but taking the absolute value of a positive number still leaves us with a positive answer. So the absolute value bars really don't make a difference in this case. And our final answer is 5. Let's try applying that rule to this problem here. Again, as this is written, we can't apply the rule that we learned up here because there's no exponent underneath here to match this index. So I've just started by bringing down this cubed root symbol. Now, in order to apply the rule that we've been practicing, we want to ask ourselves, can we rewrite negative 64 as some quantity cubed? You'll find that negative 64 is equal to negative 4 cubed. So these are equivalent expressions here. Negative 4 cubed is the same thing as negative 64. But by rewriting negative 64 this way, we now can apply that rule. These two numbers match, so they cancel. The cubed root cancels the cubed power because they're inverse operations, and that leaves us with negative 4. Now, do we need absolute value bars around our answer? No, because when the index is odd, you do not put absolute value bars around your answer. So our final answer here is negative 4. Next, we're going to learn how to solve problems involving fractional exponents. Now, another way to say fractional exponent is rational exponent. In math, the word rational is used a lot to mean fraction. So we would say that these problems, for example, have rational exponents. We're going to start with a definition. If you have a raised to the 1 over n exponent, this is equal to the nth root of a. So in this lesson, we're studying radicals, and this is why we'll see problems involving fractional exponents in this lesson, because anytime you have a problem with a rational exponent, in other words, a fractional exponent, you can always rewrite that problem using radicals. I just want to take a minute or two to show you some of the reasoning behind this rule so you can get an idea of where this rule came from. So let's suppose we came across this problem, 9 to the 1/2, and we'll pretend we didn't yet know this rule. How could we figure out what this is equal to? Well, often in math, if you're trying to solve a problem, it can be helpful to rewrite that problem in a different way. 9 can be rewritten as 3 squared. So instead of writing 9 to the 1/2, we can rewrite that problem as 3 squared to the 1/2. These are equivalent since 9 is equal to 3 squared. But when we rewrite the problem like this, we can suddenly solve it because we know our rules of exponents. When you raise an exponent to an exponent, you multiply. So this would be equal to 3 to the 2 times 1/2. And 2 times 1/2 gives us 1. So this would be equal to 3 to the 1, or in other words, 3. Let's try another similar problem. Let's say you were trying to solve the problem 8 to the 1/3, but you didn't know how to compute problems involving fractional exponents. And we'll pretend we didn't yet know this rule. Well, again, let's rewrite this problem in a different but equivalent way. 8 is equivalent to 2/3. So 8 to the 1/3 would be equivalent to 2/3 to the 1/3. Now we can calculate this because we know when we raise an exponent to an exponent, we multiply. So this would give us 2, and 3 times 1/3 will give us 1, which leaves us with 2. So if you do lots and lots of problems like this, you'll notice a pattern. 9 to the 1/2 is equal to 3. Another way we could get the answer 3 would be to take the square root of 9, where again the implied index here is a 2. 8 to the 1/3 is 2. Another way to calculate that would be to take the cubed root of 8. And this works anytime you have a fractional exponent with 1 in the numerator. You can rewrite the problem by just putting this base underneath a radical, and then your denominator becomes the index. So now that we've seen some of the reasoning behind this rule, Let's look at some examples. And again, while it might be tempting to just type these into your calculator to get the answer, we need to know how to do these types of problems by hand so that we're prepared when we start introducing variables. I'm going to start by just color coding this. Anytime you have a fractional exponent, we can always rewrite it as a radical by putting our base underneath a radical. And then whatever your denominator is, that becomes your index. So 2 becomes our index here. And again, when the index is a 2, you don't have to write it. Now we want to compute the square root of 16. You likely can compute this mentally, but I'm going to practice that shortcut that we learned on the previous page. To compute the square root of 16, I'm going to rewrite 16 as some quantity squared, because then this squared will match the square exponent and they'll cancel. 16 can be rewritten as 4 squared. Now, since this square root matches this square, the square root and the square cancel each other out, and we're left with 4. Now we learned when the index is even, we need to put absolute value bars around our answer, but the absolute value of 4 is just equal to 4. Let's try this problem here. Again, I just started by color coding the original problem. Now, anytime you see a rational exponent, you can always rewrite it as a radical. To do that, we write the 343 underneath a radical symbol, and then whatever our denominator is, that becomes the index. So our index here is a 3. Now, we could draw those pink boxes here to solve this, but instead I'm going to use the shorter approach that we've learned. Since our index is a 3, we want to rewrite 343 as some quantity cubed, because then the 3 and the cubed will cancel each other out. You might have to test out a few numbers on your calculator, but you'll find that 7 cubed is equal to 343. Now, since we rewrote 343 as 7 cubed, the cubed root and the cubed power are inverse operations, so they cancel out, and we're left with 7. And since this is an odd number here, we don't have to worry about absolute value bars. Now, before we continue on, I just want to rewrite here 2 of the important rules that we've been using. On the first page, we learned that if the index is even, the radicand cannot be negative. We also learned that if the index is odd, the radicand can be positive or negative. You'll have a solution either way. Then on page 3, we learned another important rule. We learned that when these 2 quantities match, if n is even, then these matching quantities cancel and we're left with a. But when n, the index, is even, we have to put absolute value bars around our answer. We also learned on page 3 that if these matching quantities here are odd, then they cancel out, but our answer is just a. We don't need absolute value bars. We're going to use both of these rules in problems 18 and 19. So to solve a problem involving rational exponents, we're going to rewrite it using radicals. I just started by color coding this original problem. Now, whenever you see a rational exponent, we can always rewrite it as a radical. So we'll start by drawing our radical, and we'll put negative 256 underneath the radical, and then the denominator becomes our index. Now let's review this rule here. If the index is even, the radicand cannot be negative. Since this index is even, there's going to be no solution here. Let's take a look at this example here. And again, I've just color-coded the original problem. Anytime you see a rational exponent, we can always rewrite it as a radical. We'll put the negative 216 underneath the radical, and then we put the denominator as our index. Now, let's look back at this rule here. The index is odd, and when that's the case, the radicand can be positive or negative. So here our index is odd, and even though our radicand is negative, we'll still have a solution. To find the solution, let's use this rule here. So we want to rewrite negative 216 as some quantity cubed, because then the cubed root and the cube will match and they'll cancel. You might have to try a few numbers on your calculator, but you'll find that if you take negative 6 and cube it, you get negative 216. So we have a 3 and a 3, they match, and so the cubed root and the cube cancel, and we'll be left with negative 6. Now, do we need absolute value bars? No, because if the index is odd, we do not use absolute value bars. Now, we've practiced taking a problem involving a rational exponent and to rewrite it using a radical. Now we're going to go in the reverse direction. We'll see a radical and we'll rewrite it using a fractional exponent. So anytime you have a radical, you can rewrite it using a rational exponent. Start by writing the base. In this case, the base is 9z. Then identify the index. The index here is a 3. We always write the index as the denominator of our fraction. Now be very careful here because this is incorrect. Since this cubed root applies to the whole 9z, we need to add these parentheses here to ensure that this exponent's being applied to this whole 9z. Next, let's rewrite this expression using a fractional exponent. We'll start by writing this base a cubed b over 7. Our index is a 5, and so when we write this with a fractional exponent, the index 5 goes in our denominator. Now again, since this radical applies to this whole expression, we need to apply our fractional exponent to this whole expression. And to do that, we'll put this whole expression in parentheses. Now, we've seen how to rewrite fractional exponents as a radical, but only fractional exponents where the numerator is a 1. What if you have a fractional exponent where the numerator is not 1? We're going to look at that type of problem on the next page. Let's start by writing the rule, and then we'll look at some examples. If you have a rational exponent and the numerator does not need to be 1, we can always rewrite it using a radical. To rewrite this using a radical, we put the a underneath the radical symbol. Like we learned on the previous page, the denominator always becomes our index. And actually, there are 2 correct positions you can put the m in your radical form. We can put the m as the exponent underneath the radical, and we're going to call this form 1. But you could also rewrite this expression in an equivalent way, and we'll call that form 2. Form 2 starts off the same way. To rewrite this expression as a radical using form 2, we start by drawing the a underneath our radical symbol. Then the denominator is always written as our index. Now the numerator, m, in form 1, we put as an exponent underneath our radical. But instead, we could have written m as an exponent outside of our radical, like this. Form 1 and form 2 are equivalent. Both forms can always be used, but we're going to see down below that form 2 is often the easier form to use. So while form 1 and form 2 can both always be used, we're going to rely mostly on form 2. Now again, these rules might seem completely random, but they're not. Mathematicians derived these rules using basic logic that we can understand. Let's quickly look at how mathematicians derived form 1. So this expression here, which is the same expression right here, could be rewritten like this, because remember the rules of exponents tell us when you raise an exponent to an exponent, you multiply. So if we multiply m times 1 over n, that gives us m over n. So these are equivalent. Now we learned on the previous page that when you have a fractional exponent, you can always rewrite it as a radical. If we want to rewrite this as a radical, this is our base, so we'll put a to the m underneath our radical symbol. And then if 1 over n is our fractional exponent, we always put n is the index of our radical. We've just derived form 1. We can quickly derive form 2 as well. Let's start with this general expression. And again, I'm going to use the laws of exponents to rewrite this in an equivalent way. This is equivalent to this, because anytime you raise an exponent to an exponent, you can multiply those exponents together to simplify. And if you take 1 over n times m, you get m over n. Now, the rule on the previous page told us that we can rewrite this fractional exponent using a radical. And let's start by ignoring this m, and we'll just focus on a to the 1 over n. We can rewrite a to the 1 over n by putting a underneath the radical, and this denominator n becomes our index. So we've rewritten a to the n as the nth root of a. Now, this is supposed to be raised to the m exponent, so we need to now raise this to the m exponent. And sure enough, we've now just derived form 2. Now let's try some examples where we practice using form 1 and form 2. Let's start with form 1, and I've just copied this original problem, but I've color-coded it. Notice for this problem, you might not know how to compute 4 to the 3/2 by hand, but when we rewrite it using a radical, we'll be able to compute it by hand. Anytime you have a fractional exponent, you can always rewrite it using a radical. If we rewrite this using form 1, the base 4 goes underneath the radical. The denominator is always our index of our radical. And if we use form 1, we put the numerator as an exponent underneath the radical. So in form 1, we'll put the numerator 3 as an exponent underneath the radical. Now that we've rewritten it using form 1, let's actually compute this. Now notice these two numbers do not match, so they will not cancel each other. To solve this, we're going to need to compute 4 cubed, and 4 cubed gives us 64. Now, you might be able to compute this mentally, but just to practice what we've learned, to solve this, we want to rewrite 64 as some quantity squared, because then the square root and the square will cancel out. We can rewrite 64 as 8 squared, and now the square root and the square match, so they cancel, and we'll be left with 8. And remember, when this index is even, we technically need absolute value bars around our final answer, but the absolute value of 8 is just equal to 8. Now let's solve the same problem using form 2. I've started by just color coding the original problem. Now to rewrite this using form 2, we start by putting this base underneath the radical. The denominator is always our index, and if we use form 2, we write the numerator as an exponent outside of the radical. So the numerator 3 can be written as an exponent outside of the radical. Now let's compute this. First, let's work inside these parentheses. The square root of 4 is 2. And then we'll bring down the 3 exponent, and now we can compute 2 cubed, which gives us 8. Notice that form 1 and form 2 both always give you the same answer. Let's try another example. This example is going to demonstrate why form 2 is often the much easier form to use. We'll start with form 1, and I've started by just color coding this original problem. To rewrite this using form 1, we start by putting the base underneath the radical. The denominator is always written as our index of our radical, and if we use form 1, the numerator is written as the exponent underneath the radical. So we'll write 4 as the exponent underneath the radical. Now, these numbers do not match, so they do not cancel. The only way to solve this would be to compute 32 to the 4th. If you compute 32 to the 4th, you get 1,048,576. This is why form 1 is often the harder form to use, because if you use form 1, you can end up with very large numbers underneath the radical. If we proceed to try to solve this, we would like to rewrite this number as some quantity to the 5th, because then the 5th root and the 5th exponent would match and they'd cancel. So it probably will take you a while on your calculator to figure out how to rewrite this number as some quantity to the 5th. Eventually you'd figure out that 1,048,576 can be rewritten as 16 to the 5th. But I wrote here that this is quite difficult, and we'll see that form 2 is actually much easier. But if we proceed, now that these numbers match, they cancel, and we'll be left with 16. And remember, when this matching number is odd, you don't have to ever use absolute value bars. Let's solve this problem using form 2, and we'll see that it's much easier. To rewrite this using form 2, we start by putting the 32 underneath the radical. The denominator always becomes our index. And when we use form 2, we put the numerator as an exponent outside of our radical. So we'll put this numerator as an exponent outside of our radical here. Now, we want to first evaluate inside these parentheses. To compute the 5th root of 32, let's see if we can rewrite 32 as some quantity to the 5th, because then the 5th root and the 5th exponent will match and cancel. 32 can be rewritten as 2 to the 5th. So now that we've rewritten 32 as 2 to the 5th root and the 5th power match, so they cancel, and we'll be left with 2. And now we've evaluated inside the parentheses, but we still need to raise it to the 4th. And 2 to the 4th gives us our final answer of 16. Notice again, form 1 and form 2 give us the same answer, but in form 1 we had this terribly big number to deal with, and in form 2 we had much smaller numbers that were easier to work with. So while it's important to be familiar with both form 1 and form 2, from now on I'm going to use form 2 to solve problems like these in an effort to avoid really big ugly numbers. Let's take a look at these next 2 examples. Notice if you're asked to evaluate an expression that involves rational exponents, the way we evaluate or compute it is by rewriting it as a radical. And anytime you have a fractional exponent, you can always rewrite it as a radical. I've started by just color coding this original problem. To rewrite this fractional exponent using a radical, we can use either form 1 or form 2 that we learned on the previous page. But I'm going to pick form 2 because it often avoids the really large numbers that you can get with form 1. We'll start by putting the negative 512 underneath our radical. The denominator is always written as our index, and then when we use form 2, we put the numerator as an exponent outside of our radical. Now, I'm going to just ignore this exponent for the time being so we can focus on evaluating this expression inside the parentheses. To evaluate this, let's try to rewrite negative 512 as some quantity cubed. You'll find that negative 512 can be rewritten as negative 8 cubed. And I'm going to bring down this 4 exponent so we don't forget about it. Now, if we still focus inside these parentheses, the cube root and the cubed power are inverse operations. They cancel. We're left with negative 8. Now, do we need to put absolute value bars around here? Remember, when the index is odd, you do not use absolute value bars. So we'll keep this inside the parentheses and we'll bring down the 4, but notice we did not add absolute value bars. Lastly, we want to compute negative 8 to the 4th. That will give you 4,096. Let's try another example together. Again, I've started by color coding the original problem. And to evaluate an expression like this, we want to rewrite it using radicals. We can use either form 1 or form 2, but since form 2 is often the easier form, I'm going to use form 2. For form 2, we put the base underneath the radical. We always put the denominator as our index, and then the numerator becomes an exponent outside of our radical. Now let's focus on evaluating this expression inside the radical. Notice our radicand is negative and our index is even. We learned on page 1 that if your index is even, the radicand can't be negative. So since we have an even index with a negative radicand, there is no solution. Now we've practiced rewriting rational exponents using radicals. Now we're going to go in the reverse direction and we're going to practice rewriting radicals using rational exponents. This problem here is written using form 1 since this exponent is underneath the radical. Anytime you have a radical, you can rewrite it using rational exponents. To do that, we take our base and write it here. Then we put the index in the denominator of our fraction, and this exponent goes in the numerator of our fraction. This radical is again written using form 1 since the exponent is underneath the radical. To rewrite this using rational exponents, we start with our base 7xy, and we'll keep the parentheses around it to ensure that our fractional exponent applies to this whole base. Then the index always goes in the denominator of our fraction, and this exponent goes in the numerator. Both of these radicals are written using form 2, since the exponent is written outside of the radical. To rewrite this radical using rational exponents, we'll start with the base y, z. The index always goes in our denominator, and this exponent always goes in our numerator. Now be careful, this answer is not correct because the radical applies to the whole yz. So in order to make sure that this fraction is applying to the whole yz, we need to add parentheses around it. And let's try this last example. We'll start by writing our base 25xy over 8. And then let's add parentheses around it. And then the index becomes the denominator, and this exponent becomes the numerator. Now, before we look at the last page, let's quickly review. First, we learned that any fractional exponent can be rewritten as a radical. If you have a 1 in the numerator of your fractional exponent, to rewrite it as a radical, you just put the denominator as your index. If the numerator of your fraction is not 1, then you can rewrite your fractional exponent in radical form using either form 1 or form 2. Now, the last type of problem that we need to investigate is what if you have a fractional exponent that is negative? In my 4.2 video, we learned that anytime you have a negative exponent, you can rewrite the problem using positive exponents. If the quantity with your negative exponent is in the numerator, you pick up that quantity and move it to the denominator. And when you do that, the exponent becomes positive. And if you have nothing left in the numerator, we put a 1 in the numerator. If, on the other hand, the quantity with your negative exponent appears in the denominator, to rewrite this problem using only positive exponents, we pick this expression up and move it to the numerator, and that leaves us with x to the positive 3. Now we're going to use this exact same rule. The only difference is that we're not going to have whole numbers, we're going to have fractions for our exponents. Let's start by writing the general rule, and then we'll look at some examples. If you have an expression involving a negative exponent, we can rewrite this using positive exponents by picking this up and moving it to the denominator. And when we move that expression to the denominator, the exponent becomes positive. If our negative exponent is in the denominator, we can pick this quantity up and move it to the numerator. And when we move it to the numerator, the exponent becomes positive. Now let's use this rule to help us solve some problems. In general in math, if you have a problem involving negative exponents, we typically rewrite it using a positive exponent. And that's what we're going to practice here. To rewrite this expression using positive exponents, we could picture this as being over 1. So the negative exponent is in the numerator. So to rewrite this using positive exponents, we're going to pick this up and move it to the denominator. That will leave us with 1 over AB. And when we move this to the denominator, the exponent becomes a positive 3/4. Now for this expression here, the negative exponent only applies to the x. It does not apply to the 5. If there had been parentheses around here, then the negative exponent would apply to both the 5 and the x. But since there are no parentheses, the negative 5/6 only applies to the x. So the 5 does not have a negative exponent, so we're going to leave it where it is in the numerator. The x has a negative exponent, so we're going to pick up the x and move it to the denominator. And when we do that, the exponent becomes a positive 5/6. Next, we're going to actually evaluate, or in other words, compute these expressions. If you're trying to evaluate an expression that involves fractional exponents, we like to rewrite those fractional exponents using a radical. But you can only rewrite fractional exponents using radicals when you have a positive fractional exponent. You can't rewrite negative fractional exponents using radicals. So in order to rewrite this using a radical, first, we're going to rewrite using a positive exponent. So since this is in the numerator, we're going to pick it up and move it to the denominator. And when we do that, this negative exponent becomes a positive 1/2. Now that our fractional exponent is positive, we can now rewrite it using a radical. So we'll leave the 1 in our numerator. To rewrite this expression using a radical, we'll put the 49 underneath our radical, and then the denominator is always our index. And when the numerator is a 1, you don't have to write it in your radical. Now we're asked to evaluate, so that means we want to actually compute this. We'll leave the numerator as a 1. And the square root of 49 can be simplified to 7. So 49 to the negative 1/2 is equal to 1/7. Let's try one last example. Again, in order to evaluate fractional exponents, rewrite them using a radical. But we cannot rewrite this using a radical if it has a negative exponent. So first, let's rewrite this using a positive exponent. To do that, since the negative exponent is in the denominator, we'll pick it up and move it to the numerator. And that will give us 64 to the positive 2/3. Now that our fractional exponent is positive, we can now rewrite it using a radical. To do that, we put the 64 underneath the radical. The denominator is always our index, and I'm going to use form 2 here. So I'm going to put the numerator as an exponent outside of our radical. Now the instructions say evaluate, so we want to actually compute this. Let's focus on this expression inside the parentheses, the cubed root of 64. To solve this, let's see if we can rewrite 64 as some quantity cubed, because then the cubed root and the cubed power will cancel. 64 can be rewritten as 4 cubed. And let's make sure to bring down this square. Now, if we still focus inside these parentheses, the cubed root and the cubed power match, so they cancel. So the cubed root cancels the cubed power, and we're just left with 4. And then we still have to bring down the square. And 4 squared will give us our final answer of 16.